Can you all see my screen?
Yep.
Can you all see my screen?
Yes.
All right, great, thank you. All right, so this is problem 991, and it's about a carrier mirror loaded differential pair. So the circuit looks like that. So you have the differential pair and then the carrier mirror made up of PMOS transistors at the top. And just the other thing is that this schematic is really, it's a nice way to show a small signal circuits that still show the transistor symbols. And to do that, what you do is that you pull the output resistance out of this transistor essentially. So this just becomes a pure current source, of which the source current is the same as the drain current, and that current is equal to the transconductance times the gate to source voltage. But this is still a small signal type of representation. So we are told some things about the transistors. They're essentially all the same. So they have the same GM. They are being driven by the same overdrive voltage. And they also give us some node voltages. They give us the output, the single-ended output, which we derived that last time. And then they also give us a couple of node voltages and also the inputs, okay? So what we have to do here is find out via nodal analysis, as we go around the circuit, find all the currents, and there are 13 currents, and they want us to find that in the same order as the subscript of the current, okay? So they give us this node voltage here, they give us the output voltage, they give us the node voltage at the sources of the NMOS, and they also give us the inputs. So we have to find the currents in terms of the GM and the differential input voltage. So we can see here that we have the differential input divided by 2, and then minus the differential input divided by 2. What we're going to find out is that this is a very unbalanced circuit. You'll see that the currents are not balanced, and rightfully so, because we are actually using that phenomenon of the imbalance to convert from differential to single-ended. And they also give us the direction of the currents. So we're going to also make use of that in our nodal analysis. So I just wanted to walk through the circuit. Remember, the current through the transistors, source to drain, are the GM times the VGS. So let's look at that as we work through the circuit. So they want us to follow the order of the subscript of the current. So first, we have to find this I1, which is the current through RO, the output resistance of Q4. And if we have the voltage here, they give us that voltage V out, then that current is going to be V out divided by RO. So we essentially get this expression here, half GM VID. So all the figures are going to be in terms of the GM and the VID. Now, if we go to currents 2 and 3, and we know that Q2 and Q4 are symmetrical and they are in opposite directions, that tells us that these currents in magnitude are the same, but they are in different directions. So they are adding to produce I1. So essentially, I2 and I3 is I1 divided by 2, each one of them. So that would be a quarter of GM times VID. Okay. Now, as we go next to I4, this is the drain current of Q2, which is going to be GM times VGS for Q2. So VGS for Q2 is minus VID divided by 2 minus VID divided by 4. So the magnitude is 3/4 of VID. And you multiply that times GM, so that gives you I4, which is the drain current of Q2. And since the drain currents are the same as the source currents, then I5 is also 3/4 GM times VID. As we go through I6, if we have I4 going in this direction, and then we have I6 going in this direction and I3 going in that direction, then I6 is going to be I4 minus I3. So that's 3/4 of GMVID minus 1/4 of GMVID gives us 1/2 of GMVID. And that's the current that flows through ARO. Then we have I7. So I7 is going to be, or I7 and I6 combine at this node to give us I5. Therefore, I7 is going to be I5 minus I6. So 3/4 of GM times VID minus 1/2 of GM VID gives us 1/4 of GM VID. Then next, we can calculate I8. And for that, we use again the magnitude of the VGS voltage of Q1. So that's going to be, we have here 1/2 VID, and here we have 1/4 of VID. Therefore, VGS is 1/4 of VID, and then we multiply that times GM. So that gives us I8, which is the source current of Q1. And then, since we have the same current drain source in Q1, then I9 is 1/4 of GMVID, okay? And if we see here that this is 1/4, if I8 is 1/4 of GMVID and I7 is 1/4 of GMVID, that means that I10 must be 0, flowing in that direction up through R0 of, or the output resistance of Q1. If I10 is 0 and I9 is 1/4 of GM times VID, then I11 before the node must be the same as I9. So I11 is 1/4 of GM VID. Then the current through the drain of this Q3 PMOS is going to be 1/4 of GM VID, because we can use the gate to source voltage, which is minus VID over 4 times GM. And if we use the magnitude of that, I12 gives us 1/4 of GM times VID. And since I12 and I11 are the same, that means that I13 must be 0, flowing through the output resistance of Q3. Okay. So this is an example. It shows the imbalance of the currents. So you can see how we have, for example, I5 and I8. They're not the same as part of the phenomenon that we use to, or the effect that we use to convert from differential to single-ended at V out here, okay, for this differential pair. So that's an example of a very relevant problem of chapter 9, being able to step through the circuit and recognize what's going on in terms of currents and voltages So are there any questions about this problem?
Could you go through again how you got I4 and I5?
Mm-hmm. So the drain current, I4, is GM times the gate to source voltage. And the gate to source voltage, the magnitude, is from minus VID over 2 to plus VID over 4. So that magnitude is 3/4 of VID. So you multiply that times GM and it gives you I4. Was that the question?
Yeah, thank you.
All right. So any other questions regarding this problem? All right, very good.